How's it going, Accelerated Chemistry students? This is Mr. Spurk, and this is your Chapter 10, Section 3 notes all over percent composition and chemical formulas. The relative amounts of the elements in a compound are expressed as the percent composition or the percent by mass of each element in the compound. So for example, let's look at potassium chromate. When we look at the masses of each element and divide it by the total mass of the compound, we get some percentages. So potassium takes up 40.3%, chromium takes up 26.8%, and oxygen takes up 32.9% of potassium chromate. If you know the relative masses of each element in a compound, you can calculate the percent composition of that compound. The percent by mass of an element in a compound is the number of grams of the element divided by the mass in grams of the compound, multiplied by 100%. So this is a little plug and chug equation that you can remember and use as we continue to solve for the percent by mass of an element. So let's practice a problem. When a 13.60 gram sample of a compound contains only magnesium and oxygen is decomposed, 5.40 grams of oxygen is obtained. What is the percent composition of this compound? So we want to determine the percent composition of magnesium in this compound and oxygen in this compound. So right away we know how much oxygen is obtained, so we can figure out the percent of that. So 5.40 grams of oxygen in a 13.60 gram sample times 100% gives us 39.71% oxygen. Now, we need to figure out the percent by mass of the magnesium, but we don't know how much magnesium we have, but we can solve for that. So to solve for how much magnesium we have, we can subtract the amount of oxygen in the sample from the total amount of the sample. So when we subtract these two, we get 8.20 grams of magnesium. So now we just divide 8.20 grams of magnesium by the total mass of the sample and multiply that by 100%, and we're going to be left with 60.29%. Now, if you look at our 2%, you can see that they add up to 100, which is exactly what should happen. So the subscripts in the formula are used to calculate the mass of each element in a mole of that compound. Using the individual masses of the elements and the molar mass, you can calculate the percent by mass of each element. So we can use this little equation. The percent by mass of an element is equal to the mass of element in 1 mole of the compound divided by the molar mass of that compound times 100%. So if propane, which is C3H8, is the fuel commonly used in gas grills, is one of the compounds obtained from petroleum. Calculate the percent composition of propane. So we need to determine the percent composition of carbon and hydrogen in propane. So the first thing we need to do is determine the molar mass of this compound. So just like we did in the last section, we're going to take 3 moles of carbon times 12.01 grams per mole, because that's our molar mass of carbon, and we're going to get 36.03 grams per mole of carbon in this compound. Now let's do the same thing for 8 hydrogens. So 8 moles of hydrogen times 1.01 grams per mole gives us 8.08 grams per mole of hydrogen. So when we add these two together, our molar mass is 44.11 grams per mole. So now we want to determine the percent by mass. So we want to determine what percent is carbon, and to do that, we're going to take our amount of carbon in the compound, which is 36.03 grams per mole, and divide that by the molar mass of the total compound, and multiply that by 100%. And for carbon, we're going to get 81.68%. And now we need to do the same thing for the hydrogen. So 8.08 grams per mole per 44.11 grams per mole of the compound times 100%, and that's going to give us 18.32%. So propane is 81.68% carbon and 18.32% hydrogen. So now we can use percent composition as a conversion factor. So you can use this to calculate the number of grams of any element in a specific mass of a compound. To do this, we multiply the mass of the compound by a conversion factor based on the percent composition of the element in the compound. Propane is 81.68% carbon and 18.32% hydrogen. So our conversion factors, we can assume a 100 gram sample. So 81.68% carbon translates to 81.68 grams of carbon per a 100 gram sample of propane. And the same goes for hydrogen. So when we calculate the mass of carbon and the mass of hydrogen in an 82 gram sample of propane, we're going to start with what we know, right? And we know that we have 82.0 grams of propane. And we're going to multiply that by our conversion factor for carbon. And we said that we had 81.68 grams of carbon for every 100 grams of C3H8. And when we multiply that through, we get 66.98 grams of carbon. And when we do the same thing for our hydrogen, 18.32 grams of hydrogen in a 100 gram sample of C3H8, and we get 15.02 grams of hydrogen. Now, if we look at these two numbers and add them together, they add up to our 82.0 gram sample. So now let's talk about empirical formulas. The empirical formula of a compound gives the lowest whole number ratio of the atoms or moles of the elements in a compound. An empirical formula may or may not be the same as the molecular formula. For example, the lowest ratio of H to O in H2O2 is a 1-to-1 ratio. Thus, the empirical formula of hydrogen peroxide is HO because that's the lowest whole number ratio. The molecular formula H2O2 has twice the number of atoms as the empirical formula. Notice that the ratio of H to O is still 1-to-1, however. For carbon dioxide, the empirical and molecular formulas are the same. The figure below shows two compounds of carbon and hydrogen having the same empirical formula, C to H, which is a 1-to-1 ratio, but different molecular formulas. We have ethine, which is C2H2, and styrene, which is C8H8. And you can see that there are two very different compounds. So the percent composition of a compound can be used to calculate the empirical formula of that compound. The percent composition tells us the ratio of masses of the elements in a compound. And the ratio of masses can be changed to ratio of moles by using conversion factors based on the molar mass of each element. The mole ratio is then reduced to the lowest whole number ratio to obtain the empirical formula of the compound. So let's determine the empirical formula of a compound. A compound is analyzed and found to contain 25.9% nitrogen and 74.1% oxygen. What is the empirical formula of the compound? So the first thing we can do, since we have two percentages, is and we're working with empirical formulas, is we can assume that we have a 100 gram sample. So if we have a 100 gram sample, then 25.9% nitrogen means we have 25.9 grams of nitrogen. And so we want to convert this to moles so we can get a molar ratio. So we're going to divide by the molar mass of nitrogen, and that's going to give us 1.85 moles of nitrogen. And now let's do the same for the oxygen. So 74.1% means that we have 74.1 grams of oxygen in this case. And again, we just use our conversion factor of oxygen's molar mass, and we're going to get 4.63 moles of O. Now we can't write our empirical formula as N1.8O4.63. So what we need to do is we need to divide each molar quantity by the smaller number of moles to get 1 for that element. So when we look at the moles of N and the moles of O, we see that we have a lower number of moles of N. So our second step is to take that 1.85 moles of N, divide it by 1.85 moles of N, which gives us 1. And now when we look at oxygen, we're going to say 4.63 moles of O, and we divide it by the smaller of the two, and we are left with 2.5. But we know that we can't leave a ratio as a decimal. So to fix this, we're going to multiply both of these by 2, which leaves us with a 2 and a 5. So this 2 and 5 is now our molar ratio. So our answer here is N2O5. So let's look at molecular formulas. When we look at an empirical formula and a molecular formula, we know that the empirical formula is the lowest whole number ratio. So if we look at this first row here, we see that CH is an empirical formula and its molar mass is 13. And then we look at the formula for ethyne and it's C2H2. This is still a molar ratio of 1 to 1, but this is a molecular formula because we can reduce it down to CH. And the same goes for the rest of the formulas in the chart. We can reduce them to a lower ratio. The molecular formula of a compound is either the same as its experimentally determined empirical formula, or it is a simple whole number multiple of its empirical formula. Once you've determined the empirical formula of a compound, you can determine its molecular formula if you know the compound's molar mass. So let's find the molecular formula of a compound. So if we calculate the molecular formula of a compound whose molar mass is 60.0 grams per mole, and empirical formula is CH4N. So the first thing we need to do is determine the molar mass of this compound. So we know how to do that by now, or we should know how to do that by now. So I'm going to just give us that the molar mass of CH4N is 30.06 grams per mole. So the first thing we need to do is to divide the molar mass of our molecular formula by our empirical formula. So we're going to say, so our first step is 60.0 grams per mole, and we divide that by our empirical formula's mass. Now when we divide that, that gives us a ratio of about 2. So now what we do with that 2 is we multiply that 2 by our empirical formula, which gives us a molecular formula of C2H8N2. And that's our molecular formula. So as always, all the information on these slides has been acquired and adapted from Pearson Chemistry 2012 edition of the textbook resources, the textbook resources CD, and pearsonchem.com. Have a good night, guys.